Today we are focusing in on understanding chemical formulas. A lot of the stuff I'm going to talk about today should hopefully be a review, because there's a bunch of this that you've either seen or been exposed to, and today's mostly just about making that really clear, making it really obvious to folks. So, our goals today, we're going to, I've actually already taught you about this, we're going to review the difference between a pure substance and a mixture, and then we're just going to be talking about how to read a chemical formula. So, there are 4 pieces of the chemical formula that you need to understand. You need to understand element symbols, superscripts, those are the things that go up high, subscripts, those are the things that go down lower, and coefficients, those are the things that go in front. So those are the 4 elements of a chemical formula that you, or the 4 pieces of a chemical formula that you need to understand. So let's take a moment and review some of our vocab. We have atoms, which are the particles that make up an element. We also have molecules, which are the particles that make up a chemical compound. What we're going to be talking about today are what we call chemical formulas, which is a way of saying, hey, here's all of the different elements that make up a chemical. Here's the way we connect this handful of different atoms together to create a molecule. So we need to make sure that we're really clear on the difference between the word atom versus molecule. H2O is a molecule of water that contains 2 hydrogen atoms and 1 oxygen atom. Yes, Naya?
So molecules are basically mini moles, except of different?
I wouldn't phrase it that way, because they're not going to be a huge number of things, right? It's more like a molecule is what happens when some atoms bond together. So for example, recently we talked about ionic compounds. Mostly we talked about ions and how like atoms could gain or lose electrons and become charged. But the thing about charged ions is they're effectively tiny magnets, and they'll literally snap together. You can have a cation and anions, and they'll stick together. And that's a chemical bond. Those atoms are now stuck together, and they're acting like a single particle. That single particle is a molecule. And the chemical formula is like how I would describe, hey, we've got so many of this thing and so many of that thing. All right, so again, this should still be in the realm of review. Pure substances versus mixtures. Everything's made up of particles. If I can reach into something and all the particles that I could possibly pull out are the same, that's a pure substance. So if I have pure water, then every single particle that I would pull out of that would be a water molecule. If I have a glass of orange juice, in comparison, and I reach in and pull out a particle, that could be a water molecule, or it could be a sugar molecule, or it could be a molecule of citric acid. There's lots of different things it could be, and we won't know unless I look at that individual particle. So that is a mixture. It's got lots of different things in it. So there's no chemical formula for orange juice, but there are chemical formulas for all these different chemicals that make it up. All right. So anything that has a chemical formula is going to be a pure substance. So here's some examples of chemical formulas. This has been like my quintessential example, H2O, right? What does the H stand for here? Hydrogen. What's the O stand for?
Oxygen.
Oxygen. So those are our elemental symbols. They represent what kind of atoms we've got. We also have these things. These are subscripts. This subscript tells us how many of the thing immediately before it. So this 2 means there are 2 hydrogen atoms in this water molecule. Does anyone think they can tell me how many oxygen atoms we would have? Let's go to Danny. 1. How do I know that it's 1?
Because it doesn't have a number next to it.
Because it doesn't have a number next to it. Remember that in chemistry, chemists are typically too lazy to write the number 1. So we only, if there's nothing written, then we just assume there's one of it. In the same way that in math, if I don't say if I don't give a sign for a number, I don't say positive or negative, we assume it's positive. All right, some other examples. Here we have sodium chloride. 1 sodium for every 1 chlorine. This is an ionic compound. Here we have a much bigger molecule, C6H8O7. So that's 6 carbons, 8 hydrogens, and 7 oxygens. This, by the way, is a Lewis structure for that molecule. Right now, we're just doing Lewis structures for individual atoms, but later on, we're going to learn how to represent whole molecules with them. So these little dashes represent the bonds between atoms. It says, oh, this hydrogen's connected to this oxygen, and this oxygen's connected to that carbon. So we'll get there eventually. You're not expected to understand that just yet. All right. So first, most important part of the chemical formula is the element symbol. You can find these on your periodic table. You're pretty familiar with element symbols by now. One thing I do want to take a moment and reiterate is the importance of capitalization here. A capital letter means, hey, this is a new element. So if I have something like CO, if it's a capital C and a lowercase o, then that means cobalt, which is a beautiful bluish metal. But if it's a capital C and then a capital O, these are two different elements. That would mean a carbon bonded to an oxygen. That's carbon monoxide, which is a colorless, odorless, deadly gas that's very bad if it's floating around inside your home. Carbon monoxide is created when you burn fossil fuels inside of enclosed spaces. Hey, y'all, it's a really bad idea to burn fossil fuels inside of enclosed spaces. This should be really obvious, whether it's a car with the engine running inside a sealed garage. That's incredibly dangerous because you're constantly pumping poison into the air. But also on a smaller scale, if you have things like a gas-powered stove inside your house where you're just burning fossil fuels in the same space where like kids and teenagers live and breathe, right? That's actually really bad for you. There's a lot of poisonous compounds that are created as a result of that. And we know that like living in a home with a gas stove gives children asthma, right? That is a known fact about gas stoves. Gas-powered furnaces, right? Very dangerous, especially if it's in an enclosed space where those gases can build up. And that's just from like a human health perspective. They're also very bad from a global warming perspective because, of course, a lot of these poisonous gases are greenhouse gases, and they are contributing to climate change as well. So the next time your family is thinking about getting a new stove or a new heating system, take a moment, advocate for yourself that it be something that isn't going to poison you, because gas-powered things are actually very bad. Induction stoves, that's the way to go. All right, so capitalization, super important. I will be picky about this. The ClassKick app I can't tell it to be picky about capitalization, but I will literally go back and take off points for miscapitalized element symbols. So, do y'all all feel like you can read an element symbol? Yeah. Good. All right. Our charges. This we talked about a lot yesterday. We write our charges as superscripts. So that means they go sort of up and to the right. Now, if it just says plus, how positive is that? Yossi?
1.
It's +1, right? If it just says minus, how negative is that?
1.
-1, right? So for things like a sodium cation, this plus actually means +1. This minus actually means -1. If we have something that goes a little bit more into detail, it says like -2 or 2 minus or +2 or 2 plus, that is something where we have to say how positive or how negative if it's anything but 1. Yes?
So if it's above like the letters, it's called a superscript?
Yes, if it's above the letters, it's a superscript. If it's below them, it's a subscript. And the superscript is the charge.
And the, what's the other one?
Subscript.
And what is that represent?
That's how many atoms of that element in this molecule. One more thing I want to point out about this, there's a little bit of, you can think of it as like different dialects or different accents for how chemists write their charges. Some chemists will take an ion like this oxide ion, and they might write its charge as -2. Other chemists would take the same ion and they might write it as 2-. I'm not going to be picky about this. Different chemists do it different ways. It's sort of like how, depending on whether you speak American English or British English, the word gray might be spelled G-R-A-Y or G-R-E-Y. Neither spelling is incorrect.
Wait, how do we spell it?
I don't remember which one's the American spelling versus the English
They
spelling.
sound like they sound like I feel like I've done both at some point in my life.
And meter is spelled M-E-T-R-E in British.
So
Which is weird.
neither of those is wrong, right?
Huh.
It's just a different like accent, effectively, right? So same with these. I'm not going to be picky about which way you do this. Both are acceptable.
Yours is right.
It's not a big deal to me. Either way is fine. Do we have any questions about superscripts?
Yeah.
Was there a question? I heard a yeah. I am going to point something out about the charges in ionic compounds. We only talked very briefly about the fact that these ions could snap together to form a compound yesterday. When ions form ionic compounds, they're always going to do this in a way that creates a neutrally charged compound. So for something like sodium chloride, NaCl, that works because the sodium is positively charged, Na+, it's got a charge of +1, and the chlorine is negatively charged, it has a charge of -1, Cl-. I see your hand, I'll come to you in just a moment. But let's think about if I wanted to make an ionic compound with, say, magnesium and chlorine. So magnesium chloride, there my magnesium has a charge of +2. So there's 2 positive charges from that magnesium, while the chlorine is still only -1. This compound has to be neutral. So if I've got 2 positives from the magnesium, I need to have 2 negatives from the chlorine. So I would have to have a second chlorine ion. So in an ionic compound, we always end up with a neutrally charged thing. So here I've got 2 negatives in total, 1 each from these 2 chlorines. And here I have 2 positives from my single magnesium. So we end up with a total charge of 0 in that ionic compound. We will talk about that in more detail soon. Yes?
Why do you have to cancel them out to make it neutral?
This is the reason why these things bond together. They're magnets, and the magnets are basically going to be like sticking together. So it's like the magnesium is like 2 units of positiveness, so it can attract 2 units of negativeness. So that could be a single ion with a charge of -2, or it could be 2 ions with a charge of -1.
Yeah.
All right. Any questions about superscripts or charges? Oh, Audrey, you had a question.
So you said something about superscripts for like what it is, but what exactly what does it mean it's like a subscript? Because you said what it means it's a superscript, but you didn't
Okay.
say subscript.
So superscript means it goes up here, right? And that is where our charge goes. So it's like up and to the right of the element. The subscript is like this one down here, right? It's so it's down and to the right. And that actually refers to how many atoms of this element there are, which I think is probably the next thing I'm going to talk about.
Okay.
So here we go. The number of atoms is written as a subscript. So this is methane gas. This is the gas that if you have a gas stove in your house is running through that gas line and is what the majority of what's being burned is methane, CH4. Raise your hand if you can tell me how many carbon atoms are in a single molecule of methane. Jacob. 1. We can tell this because there's no number written here, so it must be 1. Raise your hand if you can tell me how many hydrogens we've got. Raphael. We have 4 hydrogens. So 1 carbon, 4 hydrogens. So these subscripts come after the element that they're referring to. So this 4 refers just to the hydrogen.
So there'd be 4 hydrogen atoms?
Yes, there's 4 hydrogen atoms and a single carbon atom in a molecule of methane. All right, now I'm going to make it complicated. We've been talking about ions. Not all ions are made from a single element. Sometimes there are atoms that are made of more than one, or there are ions that are made of more than one ion, more than one atom stuck together. I'm going to repeat that sentence. Sometimes there are ions that are made of more than one atom stuck together. So for example, an oxygen and a hydrogen can like snap together and create an ion that we refer to as hydroxide. And this ion has a charge of -1. So let's take a moment and imagine that I want to have something like magnesium hydroxide, an ionic compound where magnesium is my cation and hydroxide is my anion. Does anyone remember the charge of a magnesium cation? Nyan?
+2.
Yeah, it's +2. So we'll have a cation that's +2. Hey, if my cation's +2 and my anion's only -1, how many of my anion do I need? 2. I need 2 of my anion. But I can't just stick a 2 right here because that would seem like it's only replying to the hydrogen. So in this kind of circumstance, what I do is I stick parentheses around this whole chunk, and then I can stick a subscript outside of the parentheses. And now this 2 refers to everything inside these parentheses. So this molecule is made up of 1 magnesium cation and 2 hydroxide anions. And the hydroxide is this whole thing, everything inside the parentheses. So raise your hand if you can tell me, in an atom of magnesium hydroxide, how many oxygen atoms are there? Raphael? There's 2, because this 2 refers to everything in here. How many hydrogens are there? 2. How many magnesiums? 1. Excellent. Does this make sense so far? Yeah. Okay. Do y'all want a harder one? No?
Sure.
Will you accept a harder one anyway?
Sure.
All right. Raphael speaking for the class and says yes. A hard one it is. All right. Let's do, here, our anion is going to be sulfate, which is an anion made out of a single sulfur and 4 oxygens. And this whole anion has a charge of -2. I'm going to stick it in parentheses. I'm going to have this sulfate bond with an aluminum cation. Aluminum has a charge of +3. And so this is the formula for aluminum sulfate. Whew. Yeah?
I have 2 questions. First, if the 3 refers to everything in the box,
Inside the parentheses.
in the
yeah.
parentheses, I mean, does the 3 change the 4?
Mm-hmm.
Does it mean it's 12?
Mm-hmm.
Okay.
All right, here's what I want. I want you all to discuss at your tables for just a moment. See if you can figure out how many aluminums, how many sulfurs, how many oxygens. So talk at your table. See if you can figure this out. All right, let's bring our attention back forward. So pause the conversation. I'm going to pick on this table back here. Can you tell me, one of you from this table back here, how many aluminums do we have in aluminum sulfate?
1.
What's our subscript here?
2.
2. So how many aluminums we got? 2 aluminums. All right, I'm going to go to this table back here. One of y'all, can you tell me how many sulfurs we have here? Emily? We've got 3 sulfurs. Because this 3 from outside the parentheses applies to everything in there. So we've got 3 sulfurs. And oh, this table back here, you two have the hard one. How many oxygens? Bear in mind that every sulfate has 4 oxygens, but we have 3 sulfates.
Oh,
And so,
12.
yeah, we got 12 oxygens. Do we have any questions about this example?
Wait, I didn't get the thing 9.
Makes sense now.
You don't get what?
I don't get what 9 is.
What 9 is?
9.
Oh, why we say 12?
Yeah.
Okay, so each molecule of this has 3 sulfates. Each sulfate has 4 oxygens. So there's 4 oxygens in the first sulfate, there's 4 oxygens in the second sulfate, and there's 4 oxygens in the third sulfate.
Oh, so in each singular one, there's 4.
Yes.
And then it's just 4 that are.
Yeah. All right, so that's our subscripts. On to our next bit, which is our coefficients. This is the part that should be fairly new. You probably haven't seen this before. The coefficient tells us how many molecules. So remember, atoms are the individual pieces that were like sticking together. The molecule is the whole thing. So here, we know, if I had this covered, H2O, a water molecule, is 2 hydrogens and 1 oxygen. But if I have 2 water molecules, each of which is 2 hydrogens and an oxygen, I have a total of 4 hydrogens and 2 oxygens. So the coefficient tells us how many molecules we've got. So I'm going to add some coefficients to these 2 problems. First, let's say, what if we have 3 molecules of magnesium hydroxide? Emily, how many magnesiums do we have?
3.
We got 3 magnesiums. Raise your hand if you can tell me how many oxygens we have. Lisa?
2.
There's 2 hydroxide. There's 2 oxygens in a single molecule of magnesium hydroxide, but we've got 3 molecules.
We have 6.
So we've got 6, absolutely. Raise your hand if you can tell me how many hydrogens. Danny?
6.
We've got 6 hydrogens. Excellent. All right, I'm going to give you, for this one I want you to discuss at your tables again. Let's say, should I make it hard? We'll have 4 molecules of aluminum sulfate. And I want you all to discuss at your tables, figure out how many aluminums, how many sulfurs, and how many oxygens.
Wait, and then is the 4 also
The 4 is how many aluminum sulfate molecules there are. So there's 3 sulfate ions in a molecule of aluminum sulfate, but we have a total of 4 molecules, each of which contains 3 sulfates, and each sulfate contains a single sulfur and 4 oxygens.
a single sulfur, so 1 times 2, 3, 3 times 3.
All right, let's raise your hand if you think you can answer the aluminums for me. Just the aluminums.
So that's
Let's go to Talia.
24.
For the aluminums,
Well,
how many aluminums, if we had 1 molecule of aluminum sulfate, how many would we have?
touches
4.
So in every 1 molecule, we have 2 aluminums.
wait, so does the 3 not apply to the...
The 3 applies to what's inside the parentheses, right? So how many aluminums in just 1 molecule? All right, but we've got 4 molecules, so a total of 8. Excellent. So we got 8 aluminums in 4 molecules of aluminum sulfate. Raise your hand if you can tell me how many sulfurs we have in 4 molecules of aluminum sulfate.
It's 48.
So how many sulfurs would we have in 1 molecule?
And one molecule is
3.
wait. Am I thinking of oxygen or sulfur?
You're thinking of the oxygens.
Oh yeah.
How many sulfurs do we have in one molecule?
One.
Well, there's one per
One per
this
thing.
ion, but there's 3 of those ions. So in one molecule
It's 3
of aluminum sulfate,
3 times something.
we have an SO4, we have an SO4, and we have an SO4. So how many sulfurs is that total?
Whoa.
Because we've got 3 of this. So we've got 1, 2, 3 of this. So how many sulfurs? How many S's? 3 S's. So that's in one molecule.
Yeah.
But then we have 4 molecules of this.
Yeah.
So that's like, that's one molecule with 3 sulfurs. Then we have a second molecule.
Isn't it 12?
Yeah, so we end up with 12, because we end up with 4 molecules. So that's another 3 sulfurs. And the last one is another 3 sulfurs. So we end up with 3, 6, 9, 12 sulfurs total.
Yeah.
All right. Raise your hand if you can tell me how many, we have 12 sulfurs. Raise your hand if you can tell me how many oxygens we have total. Emily.
48.
We have 48. Because in one molecule, in one ion, there's 4, but there's 3 ions, so there's 12 per molecule. But there's 4 molecules, so there's 12, 24, 36, 48 oxygens total. Yikes. That's harder than you're going to be asked to do today, just to be clear.
Do we have class cake?
Almost, let me finish up. So to review, the superscripts show us the charge. The subscripts tell us the number of atoms in this molecule, and if nothing's written, we assume it's 1. And the coefficient is the number of molecules. That's all for today. Y'all can go ahead and get started on today's class kit.